Hello class, and welcome to section 6.3, which is about exponential growth and decay functions. By the end of today's lesson, you will be able to identify and solve exponential growth and decay functions as well as compound interest functions. The first thing we're going to look at is the exponential growth function. So this is a type of exponential function, so where we have a variable in the exponent where the initial amount is increasing by the same amount over time. So looking at our formula here, we've got our answer is equal to our A. That's going to be our starting value or our initial amount. And then plus our times 1 plus R, which is going to be our rate of growth. You're going to see these typically written as a percent. When you plug it into the equation, it must be a decimal. So if you were given 20%, you would put in 0.2 for R. And then T, this up top part, is going to be our amount of time. So, for example, we have a radio station is sponsoring a contest. The prize begins as a $100 gift card once a day. The DJ announces a name and the person has 15 minutes to call. If the person does not call within the allotted time, the prize increases by 2.5%. So our first job here is to write an equation to represent the amount of the gift card in dollars after T days with no winners. So the first thing we're going to do here is write out the expression. So we're going to say Y equals my starting amount, which is 100, times 1 plus, that increase percentage is 2.5, but we want to turn that into a decimal, so we have 0.025. And then our time right now is T. It doesn't tell us how much time has passed. And then for part B, we want to know how much the gift card is going to be worth after 10 days. So we're going to take that equation that we had in the first part and apply a time frame of 10 days to the equation, which is going to give us an answer of $128.01. So you just plug this exactly as it is written into the calculator. So 100 parentheses, 1 plus 0.025 parentheses, and then you use that caret function to get your exponent of 10. Go ahead and try this one on your own. We plug in our initial equation. We have our initial amount, 1 plus our percent, which is now turned into a decimal. And then we're looking at 2015, so our exponent is going to be a time frame of 15 years, giving us $22,556.37. The next thing we're going to look at is the exponential decay function. This is the exact same idea as the exponential growth function, except for now we are decreasing. So we still have our starting amount, we still have our rate, which still needs to be in a decimal format, and we still have our variable standing in the exponent standing for our amount of time. Example here, we have a fully inflated child's raft for a pool is losing 6.6% of its air every day. The raft originally contained 4,500 cubic inches of air. So we're going to start by writing our equation. So I've got my Y is equal to my starting value of 4,500 times 1. We are now losing air, so we're subtracting 0.066. Changing my percent into a decimal, and then we are losing that much air every day. We don't know how many days, so I'm just going to put T for time. Now it wants us to solve as though we have had 7 days pass, so we've got our same equation, but now our T variable, we know the value of that, so we are going to plug in 7 for our time, and when we solve, that is going to give us 2,790.23 cubic inches of air left after the 7 days. Go ahead and try this one on your own. So we changed our decimal into a percent. Even though it already was a decimal, it still is a percent sign. So we still need to move it once, twice, and get 0.003 as our rate. When we plug that in, we use 10 as our exponent because it's in 2010 and it's 10 years after 2000. Notice I rounded to the nearest whole person. You cannot round that population up to say that there is another full person. You have to round it down. Last type of exponential function we're going to look at is the compound interest function. This is a type of function where a person earns interest on the initial investment and on the interest previously earned. So what this is saying is if you put $100 in the bank and then the bank pays you $10 of interest, next time they're going to pay you interest on all 110 of your dollars instead of just the initial $100 that you put in. This function looks slightly different. We still have our answer, they just call it A this time, which stands for amount, is equal to P, which means principal, which is another way for saying a starting amount of money. And then we have parentheses 1 plus. When you're paying interest, this is an increase of your money. So this is always going to be an exponential growth. It's a type of exponential growth function. This R still stands for the rate and still needs to be in a decimal format. This N value, which you see twice in the equation, stands for number of times compounded. So that's the number of times throughout the year that the bank is going to pay you money. Some common values for N that you might see, if N is 1, that's going to be annually. That's just paying it out once per year. If N is 2, it's either going to be called biannually, or you might also see it as semi-annually. If it's talking about quarterly, then X is going to equal, that N value is going to equal 4. If it's talking about monthly, that X value is going to equal 12. N value is going to equal 12. Sometimes they'll give you specific amounts, like they might say randomly that there are 8 interest periods within the year. And that would mean your N value is going to be 8. So that's the number of time compounded or the number of interest periods within a year. And then that T still stands for time. And in this case, because we are talking about something that is compounded every year, your time value must be in years. It has to have a label of years on it. If it doesn't, you're going to have to convert it into whatever amount of time that fraction of the year is. So, for example, Maria's parents invested $14,000 at 6% per year, compounded monthly. How much money will there be in the account after 10 years? So, we're going to set this up and we're going to say that A, so our amount is equal to our principal, which is $14,000, times 1 plus our interest rate, which is 0.06 as a decimal. It is compounded monthly, so that is 12 times. And then our exponent is going to be that 12 times my 10 years. Before you plug this into the calculator, you are going to want to solve this exponent and figure out what that multiplication value is. If you were to type it into the calculator like this, 0.6 divided by 12 to the 12 times 10, your calculator is going to solve this part and then multiply the answer by 10. We want the exponent to be multiplied by 10, not the answer. So make sure before you type it into your calculator, you are solving that part so that you have 14,000 parentheses 1 plus 0.06 divided by 12 parentheses, and then that caret function, and then you plug in the 120, and that is going to give us a final amount of $25,396.26. Go ahead and try this one on your own. Again, plugging into the formula, we used a monthly compounding, so that end value is 12, and we end up with $647.20. Last thing we're going to do really quick is compare the difference between interest rates that are compounded and interest rates that are not. So this says compare the investment below to an investment with the same principal, so the same starting value, the same interest rate, but it's just compounded annually. So this first one has 3 interest periods, so that means our end value is going to be 3. This compounded annually means our end value is going to be equal to 1. So if I start out with my compounded 3 times, my equation is going to be A is equal to my principal of $5,000 plus or times 1 plus 0.06 over 3 times 3 times my 12 years, making sure that you solve that exponent and get 36 when you plug it into your calculator. You are going to get an answer of $10,199.44. If we compound it annually, so just once within the year, my equation is going to start the same. So my principal of $5,000 plus 1 times 0.06 divided by 1. Anything divided by 1 stays as itself, so we can just leave it as 0.06. And then 1 times 12 is my exponent, which is just going to be 12. When I plug that into the calculator, I get $10,060.98. Now the last thing it asked us to do was compare the values, so that means we want to find the difference. So I'm going to take my $10,199.44 and subtract off the $10,060.98. And when I do that subtraction, I get $138.46 more when it is compounded 3 times. So that means if the bank pays out the interest 3 times per out the year instead of just once, you're going to end up with $138.46 more than if they just paid you interest once. Go ahead and try this one on your own. Again, the first thing we're going to do is that quarterly, that 4 times per year, end value of 4, then the annually, just the end value of 1, and we end up with a difference of $231.59 more when it is compounded quarterly. If you have questions about this or anything else from the lesson, please let me know when you get to class.